right? The R corresponding to this, the R corresponding to the whole thing. Okay, seems fairly straightforward, I guess. All right, let's do an example. Well, let's actually do the grammar for this one, the CFG. For this one has two parts. Okay? Here the strings are a sequence of n zeros followed by a sequence of n ones. Okay, so in other words, the number of zeros, number of ones are equal. You've seen this sort of thing before. And here's the reverse. You've got the ones first. So you have n ones followed by n zeros. Same number of ones as zeros. Okay, so we're asked to construct the CFG, the grammar, context-free grammar, for that language. And this language, it's explicit, you can just see. It's the union of two languages. Okay, so construct the grammar for this one and construct the grammar for that one, and then merge the two grammars. Now, in other words, you put R1 and R2, they become you union them into a bigger R, and to those rules you then add this one. Okay. All right. So let's find the rule for this one. It is here. Okay. Hold on. No, here. For this one, first one. So S1 arrow 0 S1 1. Right? You can see why that's the case, and you keep replacing S1 n times, so you get 0 0 0 n times and 1 1 1 1 n times, and eventually once you've got n of them, you'll substitute S1. S1 will be substituted by the empty string. So you're just left with those n zeros and n ones. So that is your rule set, if you like, for grammar 1, for language 1. Right? Now similarly for the second language, so its rule would be, instead of having 0, you've got 1 here, instead of 1, you've got 0 here. Okay, and again the empty string. So that rule will generate all the strings of this form, okay, for that language. All right, now so merge. So put for R, the rule set for this language with the two parts will be. You add the two rule sets. You union the two rule sets. So this one and that one, and you add. Well, there's only two of them, so you'll add this, which is that. Okay. So you've got let's see, 6. Effectively, the OR. So you've got 2 rules there, 2 rules there, 2 rules. So you've got 6 rules, and those 6 rules will generate this 2-part language. Okay. All right. Well, that's just an example. So when you have a language that's effectively the union of smaller languages, we'll find the grammars for each smaller part separately, and then merge those grammars for the grammars for each part, the grammar for each part. All right. Second tip. It's a bit of a special case. So what happens if you remember me saying earlier, context-free languages, CFLs, they're more general and more powerful than regular languages. Regular language, that was the theme of chapter 1, but they're somewhat limited in the sense that there are languages that CFLs can recognize or actually generate, and those, all those languages, they are a kind of superset of the regular languages, or rephrasing that, the regular languages are a subset of the languages that a CFG, context-free grammar, can generate. Okay, so a CFG or CFLs are more, or CFGs are more powerful. They can generate a wider range of languages than finite automata can recognize. Okay? But so in a special case, say you've got a language, and that language is a CFL. It's a context-free language, but that language is also a member of, well, it's a regular language. Okay, so put it this way: a regular language is a context-free language, or every regular language is a context-free language. I think that's true, but the reverse is not true, because the context-free languages, that set is a superset of the regular languages. But let's say we're talking about a CFL, context-free language, that happens to be, doesn't have to be, but it happens to be a regular language. Okay. So if you then know the automaton that recognizes that regular language, if you have the DFA, the machine that recognizes that regular language, because that's what regular means, right? There is some automaton that recognizes it. So then you can create the grammar, the CFG, from the machine, from the automaton. So you look at the specification, the formal specifications of this machine, this automaton, this DFA, deterministic finite automaton, that recognizes your language. Therefore, that language is a regular language by definition. Okay. So you can actually generate, you can build, construct, design the grammar, the CFG, from the machine, from the automaton. You can do that. Okay? So in a sense, I guess the key word here then is convert. You can convert that machine into a grammar. Okay, that's the sort of main idea of point 2. So if you were asked to find the grammar that generates a given language, it would be very useful to you to know that language is regular. Because if it is, there will be some, by definition, there's some automaton that recognizes it. And if you have the automaton, if you've got the formal specifications of the DFA, 5-tuple, whatever, well then, that might be the way to go. Well then you just convert this machine's automaton into a grammar. So you go from an automaton to a grammar. Okay, that's the essential idea of this second tip. All right. So how do you do that? How do you convert an automaton into a grammar? And there are a series of steps. Not too hard. And I think there's. I'm getting ahead a bit. I think there's an exercise. No, it's a homework exercise to actually show that the steps that I'll present in the next session on how to convert a DFA into a CFG, that it actually works, that the steps make sense. And how do you know it makes sense? Well, because the grammar generates the same language as the DFA recognizes. So in that sense they're equivalent. Like two machines are equivalent if they recognize the same language. A grammar and a machine are equivalent if the language recognized by the machine and the language generated by the grammar are the same language. And you have to redefine what you mean by equivalent when you're talking about a grammar and a machine. Okay?